actually, we show that this inequality holds in case A, B plus BA greater than 0. It's Jordan product. And at that time, we also, in another paper with Osaka and Hui, she's my PhD student, we consider matrix K, A plus B over 2 minus A minus B over 2 less than A sigma B. And we also show that this matrix inequality holds only in the case AB plus BA greater than or equal 0. Okay, this condition, some people told me is too strong. And in my recent paper in linear algebra and application, I consider another case of this inequality. It looks A plus B over 2 less than A sigma B plus a half A minus a half 1 minus A minus a half B A minus a half A half. And I show that this inequality holds for any AB positive definite.
What's the motivation for this inequality?
I want to avoid this condition. I don't know.
Oh, you want to weaken?
Yeah. I want to avoid this condition. So, in order to get another inequality without this condition, this inequality seems similar. What you can see here, the difference for number is the same, but for matrix it's different because I take a half to this side and I half to another side. When we do that, new inequality holds for any A and B. This inequality can be considered as something reverse Cauchy inequalities, reverse AMGF inequalities, or if we take here is geometry, so we have to reverse, right?
So your sigma is that sigma.
That's the general sigma. But I mean, if we take here geometry, so we get something reverse AMGF inequality. And okay. Later and after that, I forgot to tell you that, and also in this paper, I show if this inequality holds for any A and B, positive definite, without this condition, sigma should be identical. If we don't suppose this condition, so sigma should be identical. And it's also interesting, but I don't know. And after that, I check this result. Okay, this inequality gives some characterization of operator monotone function. So this AMGM inequality, I consider reverse AMGM, and how about this inequality? Will it give a characterization of operator monotone function? So this paper, and I also come from the classical case. So firstly, I consider this one, x plus y less than f square of xy plus 1/2 x minus 1. So similar one, right? And unfortunately, if this inequality holds for any positive or negative x and y, so function f is monotone. This if and only if f monotone. And the proof, I think is easy, but anyway, there is some interesting step. So you can see the main idea is that if I take some A and B, A less than B, right? So I need to prove there is x and y greater than 0 such that A equal arithmetic mean of x and y, and B equal geometric mean plus a half x minus y. I need to prove that. If I can find such x and y, so from this inequality I will get conclusion, right? And in the proof, actually I need to divide two steps. The first step, I need to prove only the case when A less than B and less than square root of 2A. So I prove for this case first. And for general case, I will divide interval A and B. I will divide this interval in smaller one. Okay, I can say this A0, A1, A2, and something like that. And on each interval, AI less than AI plus 1 and less than square root AI. This idea. So I will get FA0 less than FA1 less than FA2 on each interval. So I got, okay, FA less than FB, and so FE monotone. But how to apply this idea for matrices?
So basically, you want from this inequality conclude about the monotonism of the operator. Is that correct?
Of function, yes. Operator monotonicity of function. Basically, this okay. So let's consider this one. And here I take some function f, right? And I take some function f. And the main theorem is that if this inequality holds for any positive definite matrix A and B, F is operator monotone. And I use this idea. And how to apply? I can. I think I have time, right? Much time. So maybe I will give you. I will tell you the little proof of reverse Cauchy inequalities because it's nice, it's easy, and maybe this one. Okay, let's consider this inequality less than A sigma B plus half, and here 1 minus A minus a half B A minus a half, and here I have A half. Okay, I will show you the proof of this inequality. It's very easy, quite easy. So you can see here, as we show that corresponding to this sigma operator means we have some operator monotone function, right? And actually this function is defined by ft equal 1 sigma t. And from this definition, we have ft greater than minimum of 1 and t, or t the negative. And we have, that means 1 plus t over 2 minus 1 minus t over 2 less than ft. And now I will take t equal a minus a half, b a minus a half. I will replace t, apply this inequality for this matrix. And I will get so I get 1 plus a minus a half, b a minus a half over 2 minus 1 minus a minus a half, b a minus a half over 2 less than f, a minus a half, b a minus a half. And after that, I will multiply both sides of this inequality from the left and from the right hand side by a half. So I get a plus b over 2 minus a half, 1 minus a minus a half, b a minus a half over 2, and this part equal a half, and this one, and a half, right? But by definition, this nothing but a sigma f. So here's sigma f here. So that's what I got this inequalities. And I showed this inequality to Professor Hiai. He likes this proof because it's quite easy and beautiful. He told me that it's beautiful and easy to get. Okay, now I will give you a sketch of the proof of this one. Also, from this idea, from the first step, this step, we can say for I will consider first from. Okay, let's observe what is here. A less than b less than square root 2a. If a greater than strictly bigger than 0, so I can write this equal 1 less than a minus a half, b a minus a half less than square root of a, just 1, right? I can rewrite this condition in this way. So I will show that for any matrix A between 1 and square root of 2, 1, for any matrix A between this interval, I can find x, y greater than 0 such that x plus y over 2 equal 1 and A equal x, y plus 1.5 x a half, 1 minus x minus a half, y x minus a half, and x a half. And this come from this lemma come from this step, because we can use here we have worked with only one matrix, so it's not to work with scalar case, right? So it's very easy to prove, but the main I cannot give implicit form of x and y. I just to prove the existence of x and y only. And the idea is that, okay, let's consider this one. From here I can get y equal to I minus x, right? I will replace y, I will substitute y in this formula, and I get a equal x geometric mean width 2I minus x plus half x a half, and okay, so on, x 1/2. And here we have, in this part, we have only one matrix. So in some sense, scalar case, right? And here we have another matrix. I will show that so here we can consider some function ft equals square root of t 2 minus t plus 1 minus t. Actually, I consider this function. And I show that on some interval, this function is bijective. And take value on this interval from 1 to square root of 2. So that's why for any matrix A, we have inverse. We have inverse f minus A, f minus 1 of A. So I show that, yes, actually x equal f minus 1 of A. And we have y also. Yeah, that's my idea. And after that, if we have for any A less than B less than A square root of 2, I will rewrite this condition in another form, A minus a half B, A minus a half less than square root 2A. And I will apply this lemma and I will show it. Actually, for matrix A and B satisfying this condition, we can find x and y such that this geometry arithmetic mean equal A and not part equal B. And final step is that for any A and B, I will apply this observation. And I get the general result.
Now you have all this characterization. Do you have some application of this, or this is already a big text on the area that you are studying, or you have the characteristic function operator? Now, do you have any?
You mean application of this result or
Yeah,
operator
because
monotone function?
what you did, you characterize operator monotone function, right?
Yes.
That's right. So, is there any interesting application or just this is the result itself?
About this result, I'm trying to say about application, but I can tell you some application of operator monotone function. So actually, we know not too many operator monotone functions. We don't have many examples of such functions. So, okay, our function when r between 0 and 1. Another function is also useful in operator theory is t over 1 plus t, or maybe some lambda. It's also very useful, I know, because when we consider some in infinitely dimensional case, when you consider unbounded operators, using this function you can reduce to bounded operators. Because this one is, if we take 1, so this one is less than this one. So for any unbounded, you can get bounded operators. So it's quite important. Yes, exactly, I know. And how about the cubo angle theory? Cubo angle theory.
You have something like t to the r times logarithm of beta, determining beta
Yes.
such that.
Thank you. I forgot. Very important function is logarithm. T is operator monotone function. And thank you. And actually, you see, I can tell you that in quantum theory, especially in quantum information theory, many quantum quantities are defined via operator monotone function. For example, entropy. So what is entropy? A is just we can say EA equal minus trace of A logarithm of A. So this entropy, quantum entropy. And you see here, of course, here we can consider A positive, and even if they have trace A equal 1, so A is called density matrix or state in quantum theory. And they also, for example, from this, they have a relative entropy. If they have two states, A and B, they have okay, D, A, B. That's relative entropy of A and B. That is trade of A log A minus log A of A. And okay, here is log is operator monotone function, and so they also consider extend this definition for any operator monotone function. So they also consider some trace of A minus F. And I didn't tell you about the Kubo-Ando theorem, but what operator means? This theory comes from the electrical theory. Because so you have electrical network, right? And you have two kinds of parallel, or if you have parallel network, so this corresponding to some matrices. And corresponding to this network, they have consider parallel sum. Parallel sum. What is parallel sum? Okay, I can, as I remember, it might be A minus 1 plus B minus 1, something like that, right? And this, if they normalize parallel sum, they will get parallel mean. I mean here, divide by 2, also they will get mean. So motivated by this, they get general theory of means. And when means corresponding to operator monotone functions, so the connection is, I think, is very strong. And actually, I said now in quantum physics, A sigma B, and here we corresponding to some representing function, they call F equivalence of states A and B. So to consider such inequalities and how to work with operator monotone functions, I think is interesting and useful exercise.
That one has something to do with the harmonic mean.
Yes, yes. When you normalize parallel sum, you get harmonic.
You can have harmonic mean.
Yes.
So you second have this for like you call infinite dimensional, but there is something that is look like this type of work in nonlinear analysis, where they call a creative mapping, which is nonlinear. They have some sort of this type of manipulation for operating. Very interesting.
I didn't say about this theory for non-linear, just for linear. And with operator means, I think there are many kinds of interesting problems. Here we consider only for two matrices, but when we consider for more than two, it's complicated. For example, geometric mean here for square root, just we know for two matrices, but for three we don't know the form. So they call characterization something like that from differential geometry. Yes. I think basically that's what I want to talk to you. But if I have time, I can tell you some open questions related to this talk. If you want.
Yeah, we have 7.
Oh, 7.
Well, no, 5. Let's take 5 minutes. We started a couple minutes late, so 5 minutes.
Yeah. Maybe say one interesting open problem.
Yes, maybe interesting, maybe not. Okay, I will try. As I told, I recall the paper, the result of Hia and Ando. They proved that if A some F geometric mean of A and B greater than FA, sigma FB. For some sigma, then F is operator monotone decreasing function. And this, at the same time, operator decreasing function is log concave function. So this class, I think,
You mean concave down, concave upward?
and concave down. Yes. But yes, I think this result is very strong. But you see, the log convex concave function and log convex function, they are quite, I think they have many applications in optimization theory. But the class of function, when we consider matrix and operator, is the same with operator, monotone, decreasing. So it's okay, that's fine. But when I consider another, I will change, right? In their paper, they keep arithmetic mean and they change this mean. Okay, natural question is that, how about this one? When I fix this mean and change this one, what will happen? And
Well, what the motivation to look to the right hand side and modify that? Is there any?
yeah, I just raise a question and I see that actually it's difficult related to operator. Okay, related to general theory of operator monotone and operator convex function. Usually, it's easier to work with operator monotone function than with operator convex function. So you can see if I fix some f, for example, a plus b, here, right? We have this one, fa plus fb. This one is operator convex function. And to get characterization of operator convex function is complicated. It's complicated. I know one conjecture maybe is long time, it stands for a long time. So they solve that if on interval A and B and CD, right? And intersection is not empty. If the function is operator monotone on AB and on CD, so this is operator monotone on A and D. But for operator convex function, it's open. So that's why I think when we change some condition here, the problem is more difficult. And I also asked Professor here, but he also does not about that. Because in another, I say we can hear in many cases, in many papers, they consider some general conversity. That means they consider some here sigma A, sigma B, and less than FA and tau FB. When you consider different means, so you get several kinds of conversity, several kinds. And to characterize functions satisfying these inequalities, I think it's not okay. It's one side is interesting. When you get just sigma equal weighted arithmetic mean, and okay tau also weighted arithmetic mean, so you just get normal conversity, right? But how about general case? In recent paper with my PhD student, we successfully characterized for some special case. We characterized when sigma is we call early mean. That means A, B plus 1 minus lambda B about 1 minus B. This early mean for matrices. If for number they call bounding.
Lambda between 0 and 1.
What? I'm sorry.
Lambda between 0 and 1?
Lambda between 0 and 1, yes, of course. And if we have tau is poetic arithmetic mean, so we successfully characterize function satisfying this, but for general, we don't know.
Well, this inequality is interesting, this condition over here, because it looks like a segment, right?
Yes.
It's a matrix, right?
Yes, yes. Actually, on the last talk of Minchen, he also considered some LBB problems for several kinds of means, right? Maybe 3 or 4, 2 or 3 kinds of means. And corresponding to each mean, he got they got some result. And you know, means, operator means are important in quantum information theories because there are several kinds of information. Quantum informations are defined by operator means. So that's one problem. Another problem may be interesting for Professor Tom. So about operator model functions in sense of Lie theory. And I think it's also interesting. But I don't know. So probably
Okay.
I finished.
Okay, thank you. Any further questions for Hua? Well, thank you, Hua, for speaking.
Thank you.